Girls, it's a crucial section today. Today we're introducing the famous, super famous identity sheet. This right here is the essence of the entire identity chapter. We've got to master every one of these identities. Last time we introduced what identities are. We said identities are two ways of looking at it. One, identities are equations that hold true for all possible values of variables involved in the equations, except those variables that may possibly make either side undefined. That was one of the characterizations. They're formulas that are always true for all values of variables. Second characterization is an exchange rate, where every time you've got an equation, if star is equal to square, every time you bring a star, you can get back a square, or every time you bring a square, you get back a star. Those were the two different characterizations that we did last time. We also learned different techniques, famous techniques for proving identities. One was abandon the equality and work on each side separately. Another, tweak a known identity. Look at the graphs or start with something amazingly creative and brilliant. That was a great start. Now, what we got to do is really become introduced to the famous ones. You can print this off the internet, off the website. Let me tell you what the game plan is for the remainder of the semester. We're going to go through every one of these and understand it, learn what it says, how to use it, and how to prove it, so you really own it completely, yours. Then once you own it, you take a little identity, you make a little check mark on your paper, and you say to yourself, I own that. That's mine. Okay, that's the game plan for the remainder of the semester. You go through we're going to go through every one of these and try to understand what they say, how to use them, and how to prove them, how to completely own them. Got it? All right. So what we've got today for us is today we'll handle the first three paragraphs on the left-hand side. It might sound like a lot, but really, these are the easiest ones in the entire page. So we'll handle all these today, and let me tell you what the game plan is. I'll pick a couple from each paragraph, and we'll go through them, and the rest we'll leave for homework. And then what's going to happen is next time we meet, or next time you come watch the video, we'll do the Pythagoras paragraph. Next time we'll do the mother of them all, the mota paragraph. Next time we'll do, every day we'll handle one of these other paragraphs. Probably one at a time, not like today where we do three. Okay, absolutely crucial chapter, absolutely crucial famous sheet here. Okay. Actually, maybe we'll just do the first two chapters. Let's start off with the first one. The first one says that these are called definition identities. That's because they follow the definition. There's almost nothing to prove. For example, the first four, let me show you what they say. The first one says that sine of any angle theta will be the ratio of the opposite over the hypotenuse. Of course, the implication is that is the opposite of a hypotenuse on the reference triangle for theta. And how would you prove this? Well, this one is not one that we particularly are going to do much on the proving, because this is true by definition of sine theta. So this is not an identity that we have to prove. This is actually a definition of sine of theta. And so you could put a little check mark on that one, saying, I know why that's true. That's by the definition of sine theta. Put a little check mark on the tangent. You know that the tangent is opposite or adjacent by definition. Put a little check mark on that one. Put a little check mark on that one. Let's try one of these more interesting ones. Famous identity. Tangent of theta is equal to sine theta over cosine theta. Why in the world would that be? Let's see. Tangent theta is equal to sine theta all over cosine theta. And the question is why? Well, first of all, understand what it means. It means that we've got an exchange rate. Every time you bring a tangent theta to the table, you can exchange it. You can exchange it for a sine theta over cosine theta, or vice versa. What's up, Diego? So this means that every time you bring a tangent theta, you can exchange it for sine theta, cosine theta, so long as the angle matches. Among other, and this is true for all possible angles, again with some minor exceptions. So for example, if you could go backwards, so if you have sine of 30 over cosine 30, you could exchange that for a tangent 30. They are the same thing. And this will hold true for all possible angles theta, except for the ones where they make the bottom 0, because either side wouldn't be defined for those angles. So if we exclude those, this is a nice identity. And the question is why? And we had several techniques to prove an identity is true. Work on each side, tweak a known identity, look at the graphs, or start with something amazingly creative and brilliant. I say we start with we work on both sides. So here's what we do: we abandon the assumption that they're equal. We say, hey, we don't know if they're equal. That's about to be discovered. We say we just work on each side separately. So here's what we do. We're going to rely on this definition. So off on the side here, I draw a. I'll do it right here off on the side. I'll draw the reference triangle for theta. Whatever it may be, you'll drop it perpendicular to the x-axis, and by definition, if this is A, B, C, by definition, wherever the reference triangle ends up, what would tangent theta be? Tangent theta would be the ratio. Which ratio is it? Well, it would be the ratio of opposite over adjacent. That's the left-hand side. Now the right-hand side, sine theta would be A. Whoa. This is A over B over A. The sine theta, sine measures ratio of opposite to hypotenuse. So this would be B over C over cosine theta. The cosine theta measures the ratio of adjacent to hypotenuse. And so there you go. This side equals that, and that side equals that. Are they equal? Well, let's see. You could multiply both top and bottom by C to cancel this C, and that would give you B over A just by doing some algebra. This is by definition. This is by doing some algebra. This is just by definition of tangent. And now I can see that B over A is the same thing as B over A, so that proves that they're equal by working on both sides. Got it? So you go to your famous sheet. You should have printed one of these by now. And you go to the first paragraph and you say to yourself, you know what? I understand why tangent of theta is equal to sine over cosine. It's just because sine is ratio of opposite to hypotenuse and adjacent to hypotenuse, and the hypotenuse cancels just algebraically, and it's the same thing as the ratio of B to A. Same thing as the tangent ratio. And so once you got that down, you just put a little check mark and say, hey, I own that one. Done. And then let's just do one more here. Secant is the inverted cosine. Let's see. Let's see why that would be. So you could, again, say, all right, secant theta. Every time I've got a secant, I can exchange it for 1 over cosine theta. Why should that be? Well, I'm going to try the working on both sides strategy here. I'll imagine a reference triangle, theta, and the sides could be A, B, C. And then you think to yourself, secant, what is the definition of secant? Definition of secant is the inverted cosine, so it would be C over A, hypotenuse over adjacent. That's by definition of secant. On the right hand side, though, 1 over cosine, well, that would be 1 over, what's the definition of cosine? Cosine is adjacent over hypotenuse. That's by definition of cosine. And then by algebra, you could flip this, and this is C over A. You take the bottom one, this is a complex fraction, you flip it just by some algebra rules. And there you go. This proves that they're in fact they are in fact equal. This equals that, and that equals that, and that equals that, and that equals that. Therefore, this one equals that one, and that proves it. And so you check, go to your little identity sheet, and you put a little check mark there and say, hey, I own that one already. Okay, I'll let you finish these other ones, the ones that don't have a check mark. Let me go to the cofunction identities and prove a couple of these. Okay, this is the cofunction identities. First, let me tell you the co story. Who put the co in all the co's? You see all the co's everywhere? First of all, you have sine, and then you have cosine. You have tangent, and then you have cotangent. Secant, and then you have cosecant. Who put these co's everywhere? Where did all the co's come from? Co this, co that. They come from the complementary angles. Who put the co in complementary angles? First of all, do you guys remember what complementary angles are? I'm sure you do, but just for kicks, let me remind you. Complementary angles are angles whose sum is 90 degrees. So, for example, if you've got a 90 degree, you've got a right triangle, and this is 10 degrees. Think, if this is 90 and this is 10, altogether they got to add up to 180. But if so if you take this one away, these two have to add up to 90. So if this is 10, that has to be 80. On a right triangle, these ones are always, of course, complementary angles. They have to add up to 90, because if these add up to 90 and that gives you 90, that gives you a nice total of 180. So this is the complementary angles. Let's see how long a door can hold the baby outside. Complementary angles. He wants hot chocolate. Alright, I gotta take care of business. Pause. Okay, so let's expand on that a little bit. Here's a complementary story. These two, on a right triangle, these two always have to be complementary. So, for example, if this one was 20 degrees, this one would have to be 70 degrees. That way they add up to 90 degrees. Of course, sometimes I forget to put the degrees. So that altogether it adds up to 180. If this one was 40 degrees, this one would have to add up to 50 degrees, and so on and so forth. But it gets more interesting when you use variables. For example, if this one was x degrees, this one would have to be 90 minus x degrees. That way they would add up to 90 degrees. If this one was theta degrees, this one would have to be 90 minus theta degrees, and so on and so forth. These two are complementary, so that's the important thing to remember here. Every time you've got theta, the complementary angle to theta would be 90 degrees minus minus theta. If you have x, the complementary degree would be 90 degrees minus x. Okay, if we define them as angles whose sum is 90 degrees. So that's what you see at all of these identities here. On one side you have the angle theta. On the other side you've got the complementary. So you got the angle theta, you got the complementary. Almost all of them you have the complementary. That's why this is called the cofunction identity paragraph. And let me get to it. Here's one way to prove it. Let's start off with this paragraph here. Let's erase this stuff. And what it says, let's take the first one, for example, the most famous one. It says that sine of angle theta is equal to cosine of the angle 90 degrees minus theta. Now, here's one way to prove it. At this point, we don't know if they're equal. So here's something creative that you can think about. One way to look at it. You say, you know what, this is just the triangle. This angle right here, if this angle is theta, assuming it's a acute angle, again, for more generalized, I'll let you think about it. But this angle, if this is theta, how much would this one be? Well, they have to add up to 90, so this would be 90 degrees minus theta. Now, let's look at it. From this point of view, from the theta point of view, you can read off by definition, let's just call these something. Let's call this side A, let's call this one B, and let's call this one C. Now, from this point of view, you could read the sine theta, which is by definition a ratio of some of these sides. Which ratio does sine theta describe? Opposite over hypotenuse. So this would be B over C. Clear? On the other hand, if you stand on the complementary angle, over here, you read the cosine ratio of this angle, which is 90 degrees minus theta. You would be reading the ratio of, from this point of view, the cosine ratio would be the adjacent, but from this point of view, the adjacent would be B. The hypotenuse would be C. So from this point of view, you can read off cosine 90 degrees minus theta is equal to adjacent over hypotenuse. And of course these are equal. B over C is equal to B over C. So this sine theta is equal to cosine of 90 degrees minus theta. And that's how you prove it. Really, an intuitive way to think about it is that what you're doing is just standing at different corners of the triangle. From this side, the opposite ratio, opposite to hypotenuse, is the same as standing on this side and reading the adjacent to hypotenuse ratio. Right? Just depends on which corner you stand. From here it's the opposite to hypotenuse. From here would be the adjacent over hypotenuse. So the in cosine means it's a complementary function. You're just reading the ratio from the complementary angle corner. That's who put the and all the stuff. It works for all the other ones as well. And so once you do something like this and you say, hey, I understand that now, you could take your little cofunction identity and put a little check mark on that. Say, I own that. Okay? And just for fun, I'll give you a different look at it. Let's think. Well, how many different ways do we have of proving identities? We got 4 ways. Work on each side, tweak an own identity, look at the graphs, start with something amazingly creative. Let's try to look at the graphs, just for fun. So let's start off with this. We want to know is cosine. We want to know in orange. It's cosine of 90 degrees minus x, the same thing as sine of x. It really shouldn't bother you whether you call these angles x's or thetas. They're just variables. So sometimes I like theta, sometimes I like x's, whatever. That part shouldn't bother you. This is what I got to prove. By the way, it also shouldn't bother you if they're swamped. To prove that sine x equals that, the same thing as proving that is equal to sine x. Anyways, for now, I thought I could try my luck with the graphing technique. So I'm going to abandon this assumption that they're equal, and I'm going to look at the 2 graphs separately. So good thing by now we're experts at graphing. We know that to graph the sine function, all we got to do is write our standard little box here and draw your graph in there. Sine goes like this. Of course, from -1 to 1, 0 to 360. And then you look at this one and say, whoa, how am I going to draw that? Well, first I'm going to do the shift last, okay? So I'll prepare it by factoring out the coefficient -1 times x minus 90 degrees. That way if I distribute this, I get -x and positive 90 degrees if I distribute this. So here's the plan. I'll draw the cosine x, then I'll draw the scaled version, cosine -x, then I'll draw the scaled and shifted version. That in these 3 steps: prep, scale, and shift. Prep, scale, and shift. So the first one, I'm just going to draw little mini versions of them, if you don't mind. Mini versions. Okay. So the first one, let me see, cosine is standard one from 0 to 360. Can you guys see that? From -1 to 1. Negative x. What in the world does that do? Positive x's become negative x's. So that becomes -360, 0, -1 to 1. And it gets flipped this way. So imagine taking this one and flipping it over the y-axis. It would end up looking as if nothing happened. That's what we call an even function. Alright, and then I got to shift from here to here. It's a shift which way? Shift to the right 90 degrees. So this would be positive 90 degrees. This would be negative 360 plus 90 is negative 270 degrees. This would be negative 1 to 1. And there's my final box with, of course, the graph looking the same. So I take my axis here, and I'm looking at my boundaries. They go from 90 to 270. They go from 1 to negative 1. Can you see that? Yeah, you guys can see it. And I make my box. And now I fit my graph as it appeared here. And now I compare. Is this graph convincingly equivalent to that graph? Think about it. Well, it doesn't quite look the same, but if you were to continue on it, let's just continue for fun. This continues over here. Now you see, and this continues over here. And this continues here. Just look at this piece right here. Look at this piece. Does that piece look the same as that piece? And the answer is yes. Okay. And so that should be a convincing argument to show using the graphs that sine of theta is equal to cosine 90 degrees minus theta. And that was nice because we actually proved it two different ways. We proved it using something a little bit creative. I wouldn't call that amazingly brilliant. Maybe just so-so. Alright, well, that was where we stand on different corners of the triangle. That was kind of a nice idea. You stand on different corners of the triangle and you're looking at the ratio, but you're just calling it different here. From here you're calling it the opposite over hypotenuse. From here you call it the adjacent. It's a pretty nice idea. That proves it one way, and then looking at the graphs, that proves it another way, just for fun. So your job is to go through every one of these and prove it using one of the 4 techniques until you feel comfortable and you own it. And not only that, but you should understand exactly what that means. That means that you can go to the exchange house, and every time you've got, for example, sine of 70 degrees. Hey, you can exchange that for a cosine, no problem. You'll get back a cosine of 20 degrees. Same thing. If you have a sine, for the other ones too, if you have tangent of 10 degrees, you can exchange that for a cotangent of the complementary angle, 80 degrees. If you have a secant, 15 degrees, you can exchange that for a cosecant of how many degrees? Well, it would be 75 degrees. If there's no co, you put the co on it and you take the complementary angle, or vice versa. That's the exchange rate. Okay? And that's the essence of this entire paragraph. By the time you get done with the homework, everything on there should have a check mark. And that's pretty nice. I think I'll stop there. That takes care of these 2 paragraphs. We'll come back another day and talk about the even odd part of the paragraph, the next paragraph. It's incredibly important, okay? Anybody who is somebody knows these identities. And with that, I think we should wrap it up. What do you guys think?